So what we were doing last time was we were talking about what happens when we deal with complex numbers. That is, we deal with or imaginary numbers. So we have an imaginary animal today because we're doing imaginary numbers. So let me just repeat very quickly. So when we have a complex number, this is something of the form a plus bi, where a and b are real numbers. And I is the square root of -1, which is a number that we don't have typically. You know, if we try and solve something like x squared plus x plus 1 equals 0, we don't find any real solutions to this. I mean, if we try this and using the quadratic formula, we would get x is -1 plus or minus the square root of 1 minus 4 over 2, which is -1/2 plus or minus the square root of -3 over 2. And in many applications, we just say there are no solutions. To be a little more precise, we say that there are no real solutions. But in many cases, we want to allow for complex solutions. So when a mathematician says real, he doesn't mean it's something you can touch or something that is actual. So in mathematics, real and actual are different meanings. This just means that there are no numbers on the number line that satisfy this. So there's no number on the number line that we can find that solves this. But in many contexts, especially and of course in mathematics, but that doesn't seem real to many of you, but also in physics, engineering, I don't know about in chemistry, probably because chemistry is just applied physics. In many applications, dealing with these complex solutions is important. So in differential equations, for example, which you need to do in biology and in chemistry and in physics and in engineering and any kind of science, even sociology, these things are relevant. So it's important to bring them up at this point because you run into it. And so I asked this last time, I think. How many of you have not dealt with complex numbers in your memory outside of this class? Oh, okay. So I taught Professor De Cataldo's, so just one. It's interesting. Maybe the other ones have broken arms. I taught Professor De Cataldo's class because he couldn't make it yesterday, and there were like 20 people who said they had never seen complex numbers, and it was a lot less people. Anyway. Okay, so we're going to deal with this. And just a brief review from last time. The way that we do arithmetic on these things is we just treat them like a polynomial. And then reduce. Reduce has an E. Using I squared equals -1. So if I want to do 3 plus 4i minus 2 plus 5i. I just do 3 minus 2 is 1, and 4 minus 5 is negative 1. And if I multiply them together, I multiply them, well, I multiply them in the ordinary way, and then I simplify. So since I have a clicker question on multiplying, why don't I ask it? How many do I have? 8. So if I multiply together 3 plus 4i times 2 minus 2i, I should get one of these numbers unless I couldn't do arithmetic this morning. You've got to, write some stuff down. Well, maybe you can do it in your head. I know there's more than 99 people here. But, okay, good. People can do arithmetic, so that's important. All right, so I don't have to go over how to do this. You just, well, maybe I do for the people who couldn't answer. Do I need to go over this? No. Okay, so you just multiply it out and then you reduce. So let's suppose instead we want to do division. So if I have a problem like let's just do the same ones. 3 plus 4i divided by 2 plus 5i. And I want to write this in the form a plus bi. We use the trick that we used when we took limits and so on. We just multiply the top and bottom by the conjugate. And because I changed this plus to a minus, then when I multiply these guys together, there's no middle term. So this will give me, on the bottom, 2 times 2 is 4, 5 times 5 is 25, so I will have minus 25i squared here, but I squared is negative 1, so on the bottom I have a 29, and on the top I get 6 minus 6 plus 8 I minus 20i, and then 4 times 5. What? No. Sorry. So here I get 6, here I get minus 15. I don't know what I'm doing. Minus 15i. Here I get 8. And here I get 20. How about minus 20i squared, just to be consistent? And so 6 minus 20 is 14, and negative 15 plus 8 is 7. So when I do division, I have a slight, yeah.
Isn't it plus 1? Is it?
Yeah, probably. Yeah. 26, just like I said. Yeah, thank you. So, okay, so we do it that way, so that's all fine and good. This is not really what I want to talk about today. I guess I should introduce just a couple more words before I move on. So this number here, there's an associated number called its conjugate. So we sometimes write it as a plus bi with a bar over the top, and it just means change the sign on this part. So it's just change the sign. Also, this number a is the real part. Just so if I use these words, and b, not bi, but b is the imaginary part. So the imaginary part of 2 minus 5i is negative 5. And the conjugate of 2 plus 5i is 2 minus 5i. The conjugate of 2 minus 5i is 2 plus 5i. Now, so This is all fine. This is no big deal. One thing to notice is if we try and think of these things, I already said there's no solutions that sit on the number line. We can't draw these things on the number line. So if I'm thinking about, say, x squared plus 1, this parabola, we usually draw the graph of it like this, and it doesn't cross 0 anywhere we can see on the real line. But we're only putting the real numbers x down here. In order to deal with the complex numbers, we have two parts. We don't have enough room to fit a plus bi on this line. So we have to actually move to what's called the complex plane. Which is usually written, so the reals we usually write as an R like this, we write as a C. Notice that if I have a number like 2 plus I can think of this as really a pair 2, 1. And we're already familiar with pairs of numbers, graphing pairs of numbers, plotting pairs of numbers. So I can think of 2 plus I as being this number, that point in the plane. And now this is not in the same plane that you usually graph your function, because all of your numbers are a whole plane. And so this parabola, in some sense, if I want to think of this as being a complex number and this as being a complex number, I put in numbers in a plane and I get out numbers in a plane. It's a little hard to draw because it's a four-dimensional picture. But anyway, we can think of these complex numbers as living in a plane like this, and the arithmetic that we do with these complex numbers, we can actually interpret in a geometric way instead of just messing with the algebraic picture. So if I wanted to add, let me just draw the same picture again. So here's 2 plus I. If I wanted to add, say, I don't know, -3. So here, for example, is, let's not do I. Yeah, sure. So here, let's do 2. So here is, say, -3 minus 2I over there, because I want to, oops, my scale's a little screwy. Okay. So there's -3 minus 2I. Yeah. Yeah. I'm having a little difficulty with plus and minus lately. So I have those points there. Obviously, you could figure out where any number I give you would fall. For example, here is 0, which is also 0 plus 0I. And notice that if I take a real number like pi, it would sit right there on that line. So the ordinary real numbers all sit along this line, which is sometimes called the real axis. And the purely imaginary numbers, like I would be right here, sit on the imaginary axis. And what's the point of drawing these little pictures? Well, you might think none. It's just because I seem to like to draw pictures. And in fact, I remember when I was in high school and I first saw this, I thought it was the stupidest thing in the world. It was just, so what? There's two numbers. You can put them in a plane. Yay for you. I didn't see any point. But there is a real point here, which I'm trying to get to. We can think of these as vectors. Now, if you've dealt with vectors in your other classes, like in science classes or so on, especially in physics, we can think of these numbers as being like vectors, So we just draw a little arrow from the origin to the complex number that sits at the point. And now addition of these numbers works the same way as addition of vectors. When you add vectors, you draw a little parallelogram. You just pick up the vector and lay it down on the head of the one you want to add it to. Oops. Somehow my picture's off. Because that's supposed to land at -1. All right, well, what happens when my scale isn't good? So I can just draw the little parallelogram corresponding to this. So addition, this point here, which is -1 plus 3i, is the same as -3 plus 2i plus 2 plus I. So if we want to add these things, we can think of it, if it's useful to you, as addition of vectors. That these guys are a displacement. Yeah, that's not very well. And similarly, we can subtract in the same way. When you subtract vectors, or when I want to negate a vector, so suppose I wanted to take the negative of 2 plus I. Negative 2 plus I is just take this vector and turn it around. Well, my scale is way the heck off. But here is negative 2 plus I, which is the same as negative 2 minus 2 minus I. And so if I want to subtract the vector, I can just take this guy and stick it on the end there. And that will tell me where it goes. Okay? So one bit of help here is we can think of these things like vectors. Now, adding and subtracting, that didn't seem to be a hard thing anyway. But we can also do these things to put the arithmetic. So there's also a relationship with polar coordinates. It's the reason that we did this right after doing polar coordinates. We can think of these numbers in polar coordinates. So if I'm looking at these as points in a plane, so here's some complex number a plus bi. I don't seem to draw with a 45-degree angle. Let's try this. Here is some complex number a plus bi. So this is a, and this is b. And as we've been doing in polar coordinates, the length of this is the square root a squared plus b squared, which we have been calling r. And there's an angle here, theta. So these two things that I've just introduced, so this number r which is the length, the distance from 0, is called the modulus which we sometimes write it as like an absolute value. It's the distance that that point is from 0. And this number theta is the argument. Not because it yells at you, but it is just called the argument of the complex number. So complex numbers, to specify a complex number, we need two things. Just like to specify a point in the plane, we need two things. We either need an x and y coordinate, or we can think in polar coordinates where we need a modulus and an argument. If we have one, we have the other, because we know how to convert. Usually we take this, unlike in polar coordinate functions, usually we take, well, we always take the modulus to be positive. So we usually make the choice that theta is between 0 and 2 pi, or maybe negative pi and plus pi, and that r is positive. Now, what's the good of that? Well, maybe it just seems like making stuff up, but the good of that is that multiplication, so addition turned out to be a fairly simple geometric object here, and multiplication also works out. I don't want to, it's done in the book, but it's sort of a bunch of nasty trig identities. Multiplication works out to be very simple if we think of these in polar coordinates. So if I have two complex numbers, suppose I have a plus bi, which is going to be, let me use this notation just for a minute, r theta in polar coordinates, and I have c plus di, which I'll use as sp in polar coordinates. Then if I take the product, which you can work out in terms of the algebra, the polar coordinates here will be multiply the modulus and add the angles. So, and you can check this if you want. I'm not going to do it. You can check this by, multiplying this thing out and then converting to polar coordinates and checking that it will work out this. You have to use some nasty trig identities and things like that. I'm going to do it in a different way.
Is that just a general rule?
This is just always true. So, I can check it for you if you want, but it'll take the rest of the class, and there'll be some trig identities, and and we don't want to do that. And you won't care anyway, right? It is in the book, it's in it. So this is all in Appendix I in the book, Appendix I. Just like the polar coordinates were in Appendix H. You have a question, Christine? Okay.
The R and the S are multiplied. Why didn't the theta and D multiply by?
Because that isn't how it works. I didn't just say this for the hell of it. It's actually true. You can check it. And if you check it, that's what you get. Now, I'm going to show you another way of thinking about it in just a second. Okay? So, now this one I can't prove for you. I could prove this at least in theory. And, it's just trig identities. So you do some trig identities. But, in fact, something that I can't do at this point because you need some of Math 127 to be able to see this. We usually write, so if a plus bi has a polar form r theta, then instead of writing polar form r theta this way, maybe I should write polar here, because I'm never going to write this notation anymore. This is actually a theorem. It's not just a thing that I'm writing down, but I have to just say it's a thing that I'm writing down. We write r e to the I theta equals a plus bi. This is the same e as the e that you already hate, the exponential. If we take the exponential function and extend it to the complex numbers, we get something like this. So that's
how we would find the complex number.
Well, except you don't know how to compute e to the I pi. So you just have to take my word for it that e to a complex number works this way. Now, if you take that as granted, this is something that one can prove by looking at, so let me try and justify this a little bit. So let me say it again in a slightly different way using this picture here. This This is the same as saying, well, let's just look the polar form. This is the radius times the cosine of theta plus I sine theta. This is just writing the polar coordinate conversion. Or, if you prefer, we can say that e to the a plus ib is the modulus times cosine of b plus I times the sine of b. They're all the same thing. And let's check this in a couple of cases that we already know. Oops, that's not right. Sorry. What's stupid? Let's check this in a couple of cases that we already know. So, for example, if I think of a real number like I already know a real number, like, I don't know, 3 e to the 3 plus 0i, well, this is e cubed, and then I have the cosine of 0 plus I times the sine of 0. Well, this is 1 plus 0i. So this is e cubed, just like we expect. So that's all good. Why did I do this? Well, let's think about this statement in this context. If I take my polar coordinates so if I want to multiply two numbers like this, now again, you can just do the algebra, but just like we always do in math, we make things harder so that they get easier later. And so here it seems like I'm making it harder, but it allows us to do harder problems easier by doing easy problems harder. Sort of conservation of misery. Anyway. Okay. So here we have, if we write this in this polar format, this is RE to some angle. And this is some other number, SE to some other angle. And now what happens when I multiply these things together? Remember, these are all numbers. I'll do an example with actual numbers in a second. So R times S is RS. And e to the, what happens when I multiply the same base? The angles add. The arguments add. So this is that statement. We multiply the lengths, the moduli, and we add the angles. Okay. So let's try this in a specific example. So suppose I want to do one where I can figure out the numbers. So let's say 1 plus I times 1 minus I. Now I can just multiply this out and see that this is 1 minus, what did I do wrong? Oh, 1 minus I squared, which is 1 plus 1, which is 2. So I can do the arithmetic quite easily in this context. But let's do it the hard way, because that's what makes us happy, is to do things the hard way. Makes me happy. You're happy to do things easily. Let's think about 1 plus I. What is the modulus of 1 plus I? If I want to plot these points, 1 plus I means go over 1 unit and up 1 unit. It's here. What is this angle? 45 degrees, or pi over 4. We have to use radians or stuff doesn't work right. So the angle is pi over 4, and the length, 1, 1, so this is square root of 2. So this is square root of 2 e to the I pi over 4. And 1 minus I, this guy, square root of 2 e to the minus I pi over 4. When we multiply them together, we add the angles, and we multiply the arguments. So when I multiply them together, this is the same thing. And this I can do in my head, but I'm writing it out. So this is root 2 times root 2, which is 2. And e to the I pi over 4 times minus e to the I pi over 4 is 0. Now, this I can actually do just by looking at the picture and saying, this angle's plus, that angle's minus, add them together, they'll be here. This length is root 2, 2. That's fine. So, multiplication is adding angles. Division is subtracting angles. So if I wanted to do the same problem, where the algebra is just a little nastier, but not much. Much time does it have? Good. So I have 1 plus I over 1 minus I, and I want to figure out what that is. And you can do the conjugate stuff in the algebra and blah, 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 but I can also just see, so I can just think in my head what this answer is, but I'll write what I'm thinking. I already know this is root 2 e to the I pi over 4, root 2 e to the I pi over 4, but negative. So this answer should be, well, when I divide, I can divide these numbers, and I change the power here. So root 2 over root 2 is 1. This over this is the same as pi over 4 minus a minus. When I minus a minus, I get a plus. So this is e to the I pi over 2. What number is that? The length is 1, the angle is pi over 2. The length is 1. I'm on this circle here somewhere. The angle is pi over 2. That's I. Because this is no real number. I mean, the length is 1. R equals 1. The angle is 90 degrees. So this is I. I go out 1 unit from the origin, but I go up into imaginary land, where jackalopes live and play. What are jackalopes? It's a jackalope. It's a cross between a jackrabbit and an antelope. It's, they do weird things out west. They have weird parties in North Dakota. I don't know. Okay. So, oops, that wasn't the one. This is the one I want. Let's use this in some other contexts as well. Notice that something's cool if you're a math geek, and it just looks dumb if you're not. This also tells us we can write a very famous formula that e to the I pi plus 1 is 0. Why? Well, e to the I pi is just saying we go out a distance of 1, and we take an angle of pi, and we wound up here at -1. So this is a nice famous formula called Euler, yeah? From here to here? So from here to here, pi over 4 minus pi over 4 is e to the I pi over 4 plus pi over 4. Pi over 4 plus pi over 4 is 2 pi over 4, which is pi over 2. Oops, yeah, there's an I there. And then I had to say, what does this mean? What complex number makes an angle of 90 degrees with the real axis and has length 1? That's I. Because it makes a 90-degree angle and its length is 1. Okay, so we can do this. This is called Euler's formula, or Euler's theorem. It's spelled with a U, not with an O. With an O would mean he's from Houston, but he's German. So Euler's formula. It's a very well-known formula, and notice that like all of the famous math constants are here. We have e, we have pi, we have I, we have 1, we have 0. All the good numbers are there. 47's missing. I don't know. No square root 2. Those are less important. But anyway, we have those good numbers there. But we can also do something using this same idea. How much time do I have here? Not a lot. Maybe before I do that, so suppose I wanted to do something like, I can also easily figure out what I to the 27th power would be without multiplying, which you can do. Well, we could multiply it too. I to the 27th just says, well, its length is going to be 1, because this is 1 to the 27th times e to the 27th times pi over 4 I. Right? Maybe I should put an intermediate step. I'm sorry. I to the 27th is 1e to the pi over 2I, all to the 27th power. So that's 1 to the 27th, e to the 27 pi over 2I. So if I want to do 27 quarter turns, that means I did 6 full turns plus 3 more quarter turns. So this is, so I think here, 27 pi over 2, this is 27 quarter turns. Well, 27 is 24 plus 3 more. So it's 6 full turns plus 3 quarters. So this must be negative I. Right? Because every time I multiply by another I do a quarter turn, quarter turn, quarter turn, quarter turn. I go around 6 times, and then I go around 3 more quarters, and I'm good. So, okay. So are you with me here? Where are you? Okay. I have I is this point here. This angle is 90 degrees or pi over 2. I'm going to raise it to the 27th power. That means the modulus goes to the 27th power. But 1 to the 27th is just 1. So I can forget about the modulus. And every time I multiply by I make a quarter turn because I add the angle. So I'm going to make a quarter turn, quarter turn, a quarter turn, a quarter turn, a quarter turn, 27 times. So if I make 27 quarters, if I hand you 27 quarters, you have 675. So I have 675. You want to think in money. I hand you 27 quarters, you have $6.75. That is six whole dollars, and I have three quarter turns left over. Okay, one thing that I really want to get to, and so I had other questions and blah, 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 but I want to get through this. One other thing that actually this helps make simple, there's a lot of things that this actually makes simple, but we can also make a lot of these trig identities that just seem to be a pain in the neck. They just fall out nicely out of this relationship. We know that e to the I theta is cosine theta plus I sine theta. So this is called De Moivre's formula. French name, which I wrote down before, which is really just Euler's theorem in a different way. Suppose we square both sides of this. Right? If I square both sides of this, well, on this side, this is e to the 2I theta, or I2 theta, or whatever you want. So by De Moivre's formula, or theorem, or whatever it's called, the theorem, by De Moivre, this is the cosine of 2 theta plus, I didn't leave enough room, I times the sine of 2 theta. Right? Just plugging in. Take this part that's in front of the eye, and that becomes the angle. So this is that. But if I multiply this thing out here, then I get cosine squared theta minus sine squared theta from those parts, plus 2 cosine theta sine theta I. Yeah.
Did you do that yet?
Okay, I'm going to, which side?
Well, you just did.
This side.
Okay.
Well, I don't know. Here I'm going to take e to the I theta and square it. That's e to the 2 theta I.
Good.
Right? So if I think in terms of this formula, that's saying take 2 theta, and everywhere I see a theta here, write a 2 theta. First part. Second part, FOIL this out. I'm going to multiply this by itself. I get cosine squared. I get I squared sine squared, which is there. And I get a middle term, cosine sine twice. There's the middle term. So this is the first, middle, last. Okay? So what have we just shown? Well, if you look at that formula, this has to be true for every choice of theta that you make. So that means the thing with an I has to be equal to the thing with an I, and the thing without an I has to be equal to the thing without an I. So here is one of the trig identities that I can never remember. And the other one. Just by noticing that this part has to be the same as this part, and this part has to be the same as this part. Now, if you want, you can also get a trig identity. Oh, I guess this wasn't quite De Moivre, I'm sorry. You can also get a trig identity for the 10th angle formula. Right? But there's the double angle formula that makes your head hurt in pre-calculus. And if we wanted to do, so this is really de Moivre's formula. If I wanted, so for any n, for any choice of multiple, de Moivre's formula says that cosine n theta plus I sine n theta equals cosine theta plus I sine theta to the nth power. So you can use this to figure out trig identities of any number of multiple angles. If you want a triple angle formula, you can use this. If you want a 10th angle formula, you can use this, and so on. So on the last WebAssign homework, there's a bunch of messing around with complex numbers. One thing that one can do sometimes, since we have a couple of minutes left,